Okay, in the today's class, I will clearly explain about this magnetic potential. It is of two types. One is scalar magnetic potential denoted by Vm, and vector magnetic potential denoted by A bar. Okay, the scalar magnetic potential subject to condition J is equal to 0, that is there is no source current, and here it is subjected to the condition J not equal to 0. So what is scalar magnetic potential? It is defined as a quantity whose negative gradient gives the magnetic field intensity in the region where there is no current source. That is, current density is equal to 0. That is the statement. Okay. As per this statement, that is the negative gradient of Vm, that is minus del Vm, gives magnetic field intensity at that region. In that region, there should not be any current source. That is denoted by J is equal to 0, and the units are amperes per meter for magnetic field intensity. This is the main formula. Let us say, based on this, we have to derive, to prove that J is equal to 0 and Vm is equal to minus the integral minus h dot dl amperes, and the third one is this should satisfy, this means the scalar magnetic potential should satisfy the Laplace equation, that is del square V is equal to 0. We will prove that J is equal to 0, Vm is equal to integral of minus h dot dl, and this Laplace equation. We will do all these three now, and then move on to vector magnetic potential A bar. Let us prove now. In magnetostatics, H is equal to minus del Vm. That is as per the statement given. H is equal to minus del Vm amperes per meter. Amperes per meter. Analogous to this expression in electrostatics is, in electrostatics, that is E is equal to minus del V. This I have already covered in the earlier classes. E is equal to minus del V. Units are volts per meter. V is voltage per, that is voltage. Okay. Let us consider this equation now. Taking curl on both the sides for this equation, let us take curl on. Taking curl on both the sides, we will get del cross H is equal to, I will take minus outside, minus del cross minus del Vm. Why? Because we are taking curl on both sides. So it should be equal to minus del cross del Vm. Minus del cross del Vm. So according to, as per the identities, let us consider these identities now. Using the following identities. First one is del cross del V. Del cross del V is equal to 0. Del cross del V. So this is curl of gradient of any scalar is 0. We can write here curl of gradient of any scalar is equal to 0. So this is the identity that we are going to use. And another identity which we will use for this vector magnetic potential, that one is del dot del cross A. Del dot del cross A. That is divergence of curl of any vector A is equal to 0. This is divergence of curl of any vector is equal to 0. This is second identity which we will use for using this vector magnetic potential while finding expression for A, vector A. So this is divergence of curl of A, any vector is equal to 0. Now this one is, as per this identity, it is equal to 0. That is del cross H is equal to 0. Now why? Because this identity is similar to this. Del cross del V. Vm, here it is V is there. It is a scalar, it is also a scalar. So del cross del V is equal to 0. Minus of 0 is 0 only. So del cross H is equal to 0. Let this be equation number 1. Now according to Ampere's law, according to Ampere's circuit law, integral H dot dl is equal to H del cross H dot ds is equal to integral J dot ds. Okay, this is Ampere circuit law, which is nothing but the enclosed current, which is current enclosed current. So by considering these two now, on differentiating these two expressions on both sides, we will get del cross H is equal to J. Let this be equation number 2 now. So from 1 and 2, from 1 and 2, 1 and 2, del cross H is equal to 0 is del cross H is equal to J. So J will be equal to 0. From 1 and 2, J is equal to 0. This proved now. Proved that J is equal to 0. This one is proved. Now let us prove this expression now. Vm is equal to integral minus H dot dl amperes. Now remember these two identities. This identity is used in scalar magnetic potential, and this one is used in this vector magnetic potential for proving. Now second one now, that is Vm is equal to minus H dot dl, you have to prove. So you have to prove that Vm is equal to minus integral minus H dot dl. Well, dl is a vector, H is also a vector, but Vm is a scalar. We know that H is equal to minus del Vm, which is equal to minus del Vm. This we need to prove. Let us consider this. This is as per the statement given here, it is defined as a quantity whose negative gradient gives the magnetic field intensity in the region where there is no current source. That is, current density is equal to 0. So, I will consider this H is equal to minus del Vm. Okay, this can be written as del Vm is equal to minus H. Del Vm is equal to minus H. Let us take dot product on both the sides with respect to dl. So it will be Vm del dot dl. Del dot dl is equal to minus H dot dl. Del dot dl is equal to minus H dot dl. And integrating on both sides with respect to dl, these two will get cancelled. So remaining is Vm is equal to integral minus H dot dl. This you should understand how it is get cancelled. This is a vector and this is a del operator. Having three unit vectors, that is, it is defined as del dou by dou x ax cap plus dou by dou y ay cap plus dou by dou z az cap dot dl is dx ax cap plus dy ay cap plus dz az cap. Okay, the result of this dot product is dou by dou x ax dot ax cap dot x cap is 1, ax cap dot ay dot cap is 0. So finally it will be dx plus dou by dou y dy plus dou by dou z dz. Okay, so this can be written as, this one is nothing but del dl. So del dot dl is nothing but del dl. After finding the dot product of these two, we will get del dl. So integral del dl is equal to Vm integral del dl is equal to Vm only. Okay, this one and this one will get cancelled. So this is proved. Next, let us prove scalar magnetic potential satisfies. Let us see that how it is satisfies this Laplace equation del square V is equal to 0. Let us consider the Maxwell's equation from magnetic Gauss law. Magnetic Gauss law. Maxwell equation from magnetic Gauss law. What is the actually magnetic Gauss law? Dot integral B dot ds is equal to integral del dot B dv is equal to 0, since it is magnetic Gauss law. Because the flux enclosed by a closed surface is 0. A flux through a closed surface is 0. So let us consider this. Differentiating on both sides, we will get del dot B is equal to 0. So this is Maxwell's law. Maxwell's equation. This is Maxwell's equation. Del dot B is equal to 0. But we know that B is equal to mu 0 H and H is equal to minus del Vm. Let us substitute here now. Then it will become del dot B is mu 0 h which is equal to del dot which is equal to del dot mu 0 h is del Vm minus del Vm which is equal to take out to minus mu 0, then it will become del dot del Vm del Vm which is equal to del square which is equal to minus mu square del square Vm del square Vm del dot del Vm is nothing but del square Vm. This you can get it by finding the dot product of two del operators, that is del by del x ax cap plus del by del y ay cap plus del by del z az cap, and find the dot product of itself, then you will get del square Vm. We will get del square, and the Vm is constant here, so del square Vm we get, which is equal to 0. From this equation we get del square Vm is equal to 0. So the third one is also proved. Next we will move on to vector magnetic potential, that is A bar. Okay, this is our, let us see this now, vector magnetic potential. A bar. It is defined as a quantity. It is defined as a quantity. Defined as a quantity whose curl curl gives the magnetic flux density, gives the magnetic flux density in the region where there is current source. So there is a current source, J will not be equal to 0. That is, as per this statement, B is equal to curl of A. B is equal to curl of A, and J is not equal to 0 is the condition. That is, in the region the current source should be there, where A is what? A is vector magnetic potential. Where A is vector magnetic potential, and it is expressed as A is equal to mu 0 by 4 pi into volume integral J by R into dV. This we should prove. We'll prove this. A is equal to, A is what? Magnetic vector magnetic potential, which is equal to mu 0 by 4 pi volume integral J by R dV. Webers per meter. Units are Webers per meter. Units are Webers per meter. Proof. I'll prove this. According to magnetic Gauss law, according to magnetic Gauss law, del dot B is equal to 0. Del dot B is equal to 0. The divergence of B is equal to 0. You call it as divergence of B is equal to 0. Divergence of B is equal to 0. From the identity, del dot del cross A is equal to 0. Let this one be equation number 1 and let this be equation number 2. Del dot del cross, that is divergence of curl of A is equal to 0. So from 1 and 2, from 1 equation 1 and equation 2, this del dot B is equal to 0, del dot del cross A equal to 0. So B is equal to del cross A. B is equal to del cross A. From 1 and 2, B is equal to del cross A. B is equal to del cross A. B is equal to del cross A. Taking curl on both sides, will get, that is del cross B is equal to del cross A. Okay, del cross A. This identity is there, already proved in the vector calculus. Del cross A. This is del cross A is equal to del of del dot A, del of del dot A minus del square A, Let this be equation number 3. This one is equal to 0. Why? Because the current is constant. So for steady state current, del dot A is equal to 0. The differentiation of a constant will be equal to 0. So del dot A is equal to 0. So this equation will become del cross A is equal to minus del square A. This will substitute here in equation number 3. So that is del cross B is equal to now minus del square A. Del cross B is equal to minus del square A. To substitute here in equation number 3. According to Ampere's law, according to Ampere's law, according to Ampere's law, this del cross H is equal to J. Del cross H is equal to J. This you can prove here. That is integral H dot dl is equal to integral del cross H ds, which is equal to integral J dot ds. Del cross H dot ds. Del cross H is equal to J from this. If we equate these two, we will get differentiate on both sides. We will get del cross H is equal to J. That I have written here. Del cross H is equal to J. Del cross H is equal to J. You know that del cross B del cross B is equal to del cross H is equal to J. So from this, let us find out del cross B now. We know that B is equal to mu 0 H. So H is equal to B by mu 0. So del cross B by mu 0 is equal to J, or I'll write mu 0 J. Del cross B is equal to mu 0 J. So 3, let this be equation number 4. Equation number 4. From equation number 4, what is del cross B? Del cross B is minus del square A, which is equal to mu 0 J. Minus del square A is equal to mu 0 J. Minus del square A is equal to mu 0 J, which implies del square A is equal to minus mu 0 J. Minus mu 0 J. Minus mu 0 J. But what is A? A is a vector. So A is equal to AX cap plus AY cap plus AZ cap. AZ cap, and J is equal to vector J is equal to JX AX cap plus AY cap plus JZ AZ cap. So what is del square A now? That is del square del square AX cap plus del square AY cap plus del square AZ cap is equal to minus mu 0 into J. That is JX AX cap plus AY cap plus JZ AZ cap. Okay, as per this equation. So equating the x terms, y terms, z terms, will get del square AX is equal to, it's equating this term now with respect to x, is equal to minus mu 0 Jx. Similarly, del square Ay is equal to minus mu 0 Jy, and del square Az is equal to minus mu 0 Jz. Minus mu 0 Jz. Mu 0 Jz. But in electrostatics, we have already derived in electrostatics. Our aim is to find out this expression. Okay. In electrostatics, what is V? V is equal to electric potential at a point is equal to 1 by 4 pi epsilon into Q by R. R is the distance between the given point and the charge, that is the voltage potential at that point is given by 1 by 4 pi epsilon into Q by R volts. For del square V is equal to, I already derived this, del square V is equal to minus rho V by epsilon, rho V by epsilon, rho V by epsilon 0, epsilon naught, rho V by epsilon naught. And Q is equal to integral rho V dV. Rho V is the volume density, volume charge density, rho V. To integrate this with respect to V, you will get charge enclosed by the surface. Okay, this can be substituted here. So V is equal to 1 by 4 pi epsilon integral rho V by R dV. Okay, let us compare now these two. Compare what is V, the del square A. Ax is equal to minus mu 0 Jx, and Ay del square Ay is equal to minus mu 0 Jy, and del square Az is equal to minus mu 0 Jz. So del square Az here, del square U V is there. So you can compare A, wherever there is V, you put A. And here epsilon, mu is, wherever there is 1 by epsilon, we put mu naught, and wherever there is rho V, we put J, then we will get this equation. So here V is in place of V, we will write I is equal to 1 by 4 pi, 1 by epsilon naught is mu naught by this integral, since it is volume integral, then rho V is nothing but J, and R is as it is into dV. So we got the same equation. Okay, this is, in this way it is proved. Okay, viewers, if you are able to understand my lesson, please like, share and subscribe. Thank you.